Typically, when we're tuning the fuel delivery, we're going to be relying on a wideband lambda sensor that's fitted in either the collector of the exhaust system on a naturally aspirated engine or in the downpipe post-turbocharger if we're talking about a turbocharged engine. And in most instances, this is going to be absolutely fine. What's important to understand though is that when the lambda sensor is fitted in this way, what it's actually reporting on is the average air-fuel ratio across all of the cylinders. Let's say we've got a turbocharged 4-cylinder engine and we've got the lambda sensor in the downpipe as I've just mentioned. What we're actually doing is getting the average of all 4 cylinders air-fuel ratio. And this may mean that we have one cylinder that's perhaps a little bit rich, another cylinder that's perhaps a little bit lean, but the overall air-fuel ratio that's reported is going to be on our target. Now with a road-going car or even a moderately modified car, that's probably not going to be a concern. However, as we increase our power levels, as we increase our boost levels and we put more stress and strain on the engine, our tuning envelope becomes a little bit narrower. And what this means is, in this instance, if we've got a cylinder that's a little bit lean, this could potentially be dangerous. For this reason, when we're talking about highly strung engines pushing the boundaries for power and boost levels, it's not uncommon to look at individual cylinder fuel tuning. And this can be a little bit challenging. Back when I first started getting involved with EFI tuning, wideband air-fuel ratio controllers were prohibitively expensive, so adding one of these to each cylinder was probably not that common. And what we tended to use instead was individual cylinder EGT. We still see this as a very common technique in high-end drag engines. However, using EGT as a means of individual cylinder fuel tuning is not particularly accurate because it's not just the air-fuel ratio that affects the measured EGT. So while it's helpful, it's not going to specifically get us exactly the same air-fuel ratio on each cylinder. Before we dive into individual cylinder lambda though, we also probably want to discuss why we may see inconsistencies in the air-fuel ratio across all 4 cylinders or 6 cylinders or 8 cylinders depending on the engine we're tuning. And this really comes down to a variety of aspects. It may be the design of our inlet manifold or plenum chamber that favours airflow into a particular cylinder. It may be a case of the porting on all 4 cylinders on a 4-cylinder engine. The head porting may not give consistent flow across every cylinder. There's a variety of aspects, as you can see, that come into this. So while on face value we may expect equal airflow into every cylinder, that's really actually going to be the case. So when it comes to adding individual cylinder lambda sensors, there's a variety of options that have come up over the last few years that actually now makes it reasonably affordable. Let's have a look at a couple of options that we've got here at HPA. The first of the options we've got here is this AEM 4-channel wideband controller. So as its name implies, it can take up to 4 lambda sensors into it. This actually uses the older Bosch LSU 4.2 lambda sensor. The AEM wideband controller comes with a pre-terminated harness which makes installation simple. It's essentially plug and play, and it outputs data to either an ECU or a data logger in 2 different ways. It has an analog voltage output, which means that it provides 4 signals that range between 0 and 5 volts depending on the air-fuel ratio, and it can also output the data as a CAN message. Now, where possible, I always prefer to use a CAN-based wideband controller. The reason for this is that with an analog voltage output, the accuracy of the air-fuel ratio reading in our ECU or data logger is very dependent on ground offsets, which can easily creep in. If we've got ground offsets, this can mean that the data that we're looking at is completely nonsense, completely inaccurate. On the other hand, if we're sending that data as a CAN message, the integrity of the air-fuel ratio data is guaranteed. It won't fluctuate. We know that the reading we're looking at is the reading that the sensor is actually gathering. These days, our lives are made a lot easier in this instance because the majority of aftermarket standalone ECUs as well as dash loggers have configurable CAN templates, meaning that if we have the data that AEM provide for their CAN message template, we can replicate that in our dash logger or ECU and read that data in. So we don't need to be necessarily using an AEM ECU or dash in order to get that information in and use it for our tuning purposes. Another option we've got here is the Link CAN Lambda unit. So these are a single channel wideband controller. As their name implies, they transmit the information only via CAN, so there's no analog voltage output from these units. These also use the newer Bosch LSU 4.9 Lambda sensor. As you can see, they've got quite a small packaging size, so it's relatively easy to fit in just about any tight cramped engine bay. One of the aspects to consider when you're using a single channel wideband controller that's transmitting on CAN like that Link CAN Lambda unit is when we're starting to add multiple, the CAN ID for each individual controller needs to be set. Otherwise, essentially, we've got all 4 of those CAN to Lambda controllers transmitting information on the same CAN ID. That's not going to work very well. Fortunately, it's pretty simple and easy to set that up to suit your particular application. Now, there are a few other considerations when it comes to actually mounting our individual cylinder Lambda sensors. Obviously, these are going to be mounted in the exhaust manifold or primary runners as opposed to the exhaust system itself. The primaries, be it a naturally aspirated exhaust manifold or a turbocharged exhaust manifold, the primary diameter is obviously going to be smaller than our actual main exhaust. So with the main exhaust system, when we're fitting a Lambda sensor, generally we have the Lambda sensor extend out into the exhaust system itself. We've got here a pretty common style of exhaust weld fitting that we would use for that, and you can see it's relatively narrow, relatively short I should say, and what this means is that the tip of the sensor will end up protruding into the exhaust system. Now that's good in one way because it makes sure that the tip, which is actually doing the air-fuel ratio sensing, is out in the exhaust flow. However, when we come to a individual cylinder Lambda in configuration, that's now going to potentially pose a flow restriction to our exhaust flow. So it could actually end up hampering power. Obviously not what we want. The other aspect though is because the exhaust gas temperature, particularly pre-turbocharger, is likely to be quite a lot higher than what we would measure in the collector or the turbo downpipe. This can also dramatically shorten our sensor life. So when we are mounting pre-turbo individual cylinder Lambda, particularly, we tend to use an extended Lambda sensor weld fitting like this one here. So particularly when we are fitting the Lambda sensor pre-turbocharger, we want to extend the Lambda sensor weld bung so that it brings the sensor flush with the side of the exhaust primary. Let's have a look at the option we've got here from AEM. So we can see here the weld bung is quite a lot longer, and this positions the sensor just flush with the end of the bung. You can see it's also got these grooves machined into it, so it kind of acts as a bit of a heat sink, helping to remove heat from the sensor head and prolong sensor life. When we're talking about sensor life, this is another aspect that we see a lot of problems with in the aftermarket, and a lot of tuners complain about sensors dying after only a few weeks or a few months of use, and this is often blamed on the sensor itself. And what we actually need to understand though is these Bosch LSU sensors, the 4.2, the 4.9, these are actually an OE product that are used in factory applications. In the factory applications, obviously the manufacturer, Bosch in this case, needs to meet a factory warranty period. This might be 100,000 kilometers of use. So obviously in the factory application, these sensors aren't dying weekly or monthly, and we need to understand why that can happen. A lot of this actually comes down to the control strategy of the wideband controller. In particular, what we see with a lot of aftermarket standalone wideband controllers is that as soon as the key is turned on to power the car up, the wideband controller starts heating the wideband sensor. And what can happen, particularly on a cold start, is that the sensor will be hot. We then start the car, we get a lot of moisture going through the exhaust system, and this can quickly destroy the sensor. So we're seeing a lot of wideband controllers now getting a little bit smarter, in particular the Link CAN Lambda sensor that we've just looked at there. When we connected this up to a Link ECU, or if we're sending the right CAN messages, it actually takes engine RPM in as a CAN message, and what this allows allows the controller to do is only power the sensor when it detects that the engine is running. So this, along with the actual aggressiveness of the control strategy for the heater, can actually give us a much longer sensor life. So just something to keep in mind if you're finding that your sensors are dying very quickly. An alternative way of doing this, if you don't have a sensor that takes an RPM message, is to power the wideband controller off a relay that's activated by something like the oil pressure switch, or an auxiliary output off your ECU that only activates above a certain RPM. And this will mean again that the wideband controller doesn't start heating the sensor until the engine's actually running. Another aspect that's easy to overlook with individual cylinder lambda sensors is that the accuracy of the air-fuel ratio data will also be affected by the exhaust back pressure. Now, in a naturally aspirated engine, this might not be too big of a concern. However, if we are running pre-turbo with our sensors, then it's not uncommon to see the exhaust back pressure pre-turbocharger reach as much as double the boost pressure we're seeing in the inlet manifold. So this might be 30, 40, or 50 psi, and that's going to have a dramatic effect on the accuracy of our sensors. There's two ways to deal with this. One way is that we can completely ignore it, and we're not really looking for the specific individual cylinder air-fuel ratio number, but rather we're looking at the difference between cylinders. In this way, it doesn't really matter if the sensor is reporting air-fuel ratio or unicorns. We're just looking at the number of unicorns on cylinder 1 versus cylinder 2, 3, 4, etc., and trimming in our ECU to suit. What we're then using for our overall air-fuel ratio tuning is a single sensor that's fitted in the conventional place, either in the collector or the turbo downpipe. However, if we want to get a little bit flasher, we're seeing a lot of the controllers these days actually incorporate back pressure sensors into their control strategy and correcting the air-fuel ratio data. This requires, of course, an exhaust back pressure sensor. We've got an example here from AEM which comes with their 4-channel wideband controller kit. This is a 0 to 100 psi gauge sensor. It's plug and play with the harness that comes with the AEM controller. On the other hand, the Link Cantor Lambda wideband controller deals with this slightly differently. If you're bringing exhaust manifold back pressure into your ECU, then you can transmit that data out to the Link Can Lambda unit with a separate CAN message. If that CAN message exists, then the CAN Lambda unit will automatically correct the air-fuel ratio data before transmitting it back out to the ECU or data logger. Now, there are a few complexities around actually mounting the exhaust back pressure sensor. Understandably, we can't just fit this directly to the exhaust manifold because it's going to be quickly destroyed by the heat that exists there. So what we need to do is remotely mount that sensor, and we can connect it to the exhaust manifold collector using a length of copper or stainless tube that's coiled up to allow it to dissipate the heat before it actually reaches the sensor. Another aspect with exhaust manifold back pressure sensors is that if we look at the raw data, the signal is actually really noisy, and this is understandable because we're getting pressure spikes as the individual exhaust valves open and close. There's a couple of ways of dealing with this. We can incorporate software filtering of the exhaust manifold back pressure signal, or alternatively, there are mechanical dampers that are available that damp out the oscillations in or pressure spikes in that signal before the signal is sent to our ECU or logger. Once we've got everything configured, obviously we can now measure the air-fuel ratio on the individual cylinders, and you may be quickly surprised at exactly how much variation there is between the different cylinders. This will vary as we go through the RPM range. There might be certain RPM areas where we see quite big discrepancies, whereas in other regions, maybe higher in the RPM range, we start to see the air-fuel ratios become fairly consistent. We've fitted these to our Toyota 86 development car using the Motec M150 ECU, and if we dive into the M1 Tune software, we can see what this looks like in order to equalize our individual cylinder air-fuel ratios. While every ECU is going to look a little bit different in terms of how it deals with individual cylinder tuning, here in the M1 software we can see we've got a tab for fuel volume trim. There's a variety of trims here, but what we're actually looking at is the fuel volume trim for cylinder 1, 2, 3 and 4, and this is where we can trim each of those cylinders. Let's open this up full screen and we can see here we are looking at the fuel volume trim for cylinder 1, and we've got an axis set up for this table with inlet manifold pressure on the vertical axis, and we've got engine RPM obviously on our horizontal axis. We've got a graphical representation of what the trim table looks like, and it looks a little bit ugly there, but if we look at the actual numbers we can see in this region we're sort of talking differences of plus or minus 3% as we move higher in the RPM range here. Up at 8,000 RPM, we've got trims there of about 1.5%. If we scroll through the different cylinders here, we can see, for example, on cylinder 2, our trims are a little bit greater there, 8 to 10%, just showing you the magnitude of the sort of trims we're likely to see in order to get our air-fuel ratios all under control. So there's just a couple of options for measuring our individual cylinder air-fuel ratio, what it looks like inside of the tuning software, and how we can deal with the variations that we may find. It's important to reiterate again that this is not an essential technique for every tuning job. However, when our specific power levels rise and that tuning envelope starts to get a little bit narrower, using a technique like this can be the difference between a powerful engine that's reliable and one that's a hand grenade.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.